Hi everyone, welcome to Cultrip. So in this session, let us find the values of critical inductance, critical capacitance and critical resistance that decides the mode of conduction in case of DC to DC converter, right? So now if you observe here, we have the three converters here. So one is buck converter, boost converter and buck boost converter. So how we can identify this converter? If the inductor is placed on load side, it is a buck converter. If the inductor is placed on source side, so it will be the boost converter. If the inductor is placed in between the source and load, so it will be the buck boost converter. So it is the buck converter. So it is the buck converter, right? So it is the buck converter, and it is the boost converter, and it is the buck boost converter. Buck boost converter, right? So how you can find the conduction mode? On which parameter? So the conduction mode depends. So in case of DC to DC converters, whatever may be the converter, whether it is buck converter, boost converter, buck boost converter, the conduction modes are so continuous conduction mode and discontinuous conduction mode and critical conduction mode. Discontinuous conduction mode and critical conduction mode. Now let us see how we can find these different conduction modes, on which parameters on these conduction modes will be depends. So for example, so here these conduction modes will be depends on the nature of the inductor current waveform. So let me draw the inductor current waveform. Let me draw the generalized inductor current waveform. The inductor current waveform would be like this. So IL, let me represent with IL. So the inductor current waveform will be, so in case of continuous conduction mode, so it will be like this. So this already we have seen in the previous session. So here the inductor current will be up to 0 to dt. The inductor current will be increasing in nature, and the slope is negative in between the dt to t. dt to t. On which parameters it will depends? It depends on the so voltage across the inductance. For example, in case of buck converter 0 to dt, what is the voltage across inductance? So 0 to dt, the switch should be on condition and diode should be off condition, so that it will be the Vs minus V0. Inductor voltage will be the Vs minus dt to t. So during the off time of the switch, the diode will be on condition. So the switch should be off condition, diode should be on condition, so that VL equal to V0. So VL equal to minus V0. So VL equal to minus. So for example, in the similar manner, so you can find the boost converter and buck boost converter. So how we can find? So if I want to find the voltage across inductance in case of boost converter, so 0 to dt period, so the switch should be in the on condition, diode should be in the off condition. So this circuit is isolated. The VL equal to, for example, if I make this VL will be like this. So VL equal to, so what is the VL? So VL equal to Vs. VL equal to Vs. dt to dt. So during the off time of the switch, the diode will be in the on condition. So when diode is in on condition, switch is in off condition. So what is the VL? Vs minus V0. VL equal to Vs minus V0. Right? So now let us see this one. So when 0 to dt period, so what is the VL? So VL equal to Vs. dt to t period, that is switch is in off condition, diode is in on condition. So VL equal to minus V0. VL equal to minus. Right? So to draw the IL waveform, so we require these values. For example, if I take the buck converter, for all the three converters, the nature of the waveform will be similar. 0 to dt period, the current will be increasing. dt to t period, the current will be decreasing. So for example, if you see here, so the slope will be, in case of buck converter, what is the slope? Vs minus V0 by L. So that is positive slope. In case of buck converter, the output voltage is less than the input voltage. So that Vs minus V0 is positive. So it will be the positive slope. So here, what is the slope here? dt to t period. So the slope will be negative with the slope of minus V0 by L. In the similar manner, so all these conditions will be derived. So it will be if it is a boost converter, Vs by L, Vs minus V naught by L. In case of buck boost converter, so Vs by L the slope and minus V naught by L. So this is how we can draw the IL waveform. Now we got the IL wave. So by observing the IL waveform, so whether it is operating in the continuous conduction mode or the discontinuous conduction mode or the boundary conduction mode, how we can define, let us see here. For example, now we got the IL waveform. So on which parameters the nature of the IL waveform will be depends. Let us see. For example, IL equal to, so what is IL? So here I can represent the I max and I minimum also. For example, what is the I minimum? So this is the average IL. This is the average IL. And this will be the I max. Let me call this as I minimum. Right? So what is the IL? So what is the I max here? I max will be the IL minus delta L by 2. IL minus delta L by 2. Right? So IL plus delta L by 2. IL plus delta L by 2. So what is the I minimum? So IL minus delta L by 2. So which is the delta L, right? Which is the delta L. The current ripple, delta L. So IL minus delta IL by 2. So you will get the I minimum. So I minimum equal to IL minus delta IL by 2. IL minus delta IL by 2. So now we need to find the IL and I max. So IL and delta IL, if you know the IL and delta IL, you can find the I max and I minimum. So let us see what happens. For example, so what is I minimum? Let us see. What is I minimum? Let me write the expression for I minimum. So I minimum equal to, in case of buck converter, IL equal to I naught. The inductor current is equal to the average inductor current equal to the output current. So IL equal to I naught minus. So delta IL equal to, already we have derived. So delta IL equal to Vs into D into 1 minus D divided by LF. So here the 2 also, so it will be the 2L. So this is how I minimum can be defined. So if I write the I minimum, so I naught equal to V naught by R minus Vs into D into 1 minus D divided by 2L. So now on which values the I minimum will be depends. So here if you observe, it is depends on resistance, right? So it is depends on resistance as well as, so it is depends on inductance. It is depends on inductance and it is depends on the duty cycle also. So the I minimum value will be depends on, so the source voltage, inductance, resistance and the duty cycle. So if you keep the frequency as constant. Now, so let us see on which, if I increase the inductance, what happens? If I increase the resistance, what happens? Let us see here. For example, so if I increase the resistance, what happens if I increase the resistance? So if I increase the resistance, let me call this portion is X and let me call this portion is Y. If I increase the resistance, in that equation, increase the resistance, X will be decreases. If X will be decreases, I minimum will be decreases. For example, if I reduce the inductance, what happens? Let us see. If I reduce the inductance, what happens? The Y will be increases. So if X is constant and Y is increases, again I minimum will be reduces. So in two cases, that is, if I increase the R value or if I reduce the L value, the I minimum will be reduced. So if I increase the inductance, let us take one parameter. So if I decrease the inductance, what is happening? So the I minimum will be reduced. At some point, this I minimum will be attained to 0. At some point, the I minimum will attain to 0. So let me represent with the white color. So I minimum will attain to 0. At some point, it will be like this. So after that, if I decrease the inductance further, if I decrease inductance further. So now what happens? That inductor current, this inductor current, the diode current, so this portion will become to 0. Let me represent with the other color. So here it will be like this. And if you observe, again it will start from here. Again it will start. So if you observe these three waveforms, by observing the three waveforms, we can say that so the converter is operating in the continuous, discontinuous and the boundary conduction mode. So what is the continuous conduction mode? So this will be the continuous conduction mode. This yellow color will indicate the continuous conduction mode. So how we can define that? If the inductor current waveform is continuous and it is positive and it is always positive, so we can call this as a continuous conduction mode. If the inductor current is 0 and this red color is discontinuous conduction mode. Discontinuous conduction mode. So what is discontinuous conduction mode? In case of discontinuous conduction mode, the part of the current for some period of the time it will be equal to 0. For some period of time, the part of the inductor current will equal to 0. So during this period will be called as discontinuous conduction mode. So this white color is in between the boundary conduction mode, in between the continuous conduction mode and the discontinuous conduction mode. So which is called as critical conduction mode or the boundary conduction mode. Boundary conduction. So this white color indicates, so boundary conduction mode. This yellow color indicates continuous conduction mode and this red color indicates the discontinuous conduction mode. So this is how we can define the conduction modes. Let us see what is the critical resistance, what is critical inductance, what is the critical capacitance here. So here let us find what is the critical value of inductance. Let us find what is the critical value of inductance. So LCR, let me write this as LCR, critical value of inductance. So what is critical value of inductance here? So if you observe here, when the inductance initially, let us assume that it is operating in the continuous conduction mode. Let me write this as LCCM, continuous conduction mode, LCCM. Let us assume that, so it is operating in the continuous conduction mode. Now I am reducing the inductance value. So what happens? So the IL waveform also reducing. The IL value, the magnitude of I minimum also reducing. So the magnitude of I minimum reducing, somewhere it will get to 0. I minimum will get into the 0. So that point we can call this as LCR. So LCR, we are reducing. So still after LCR also, if I reduce, it will operate in the discontinuous conduction. It will operate in the discontinuous conduction. Now, how we can define? If I LCR, if I take the reference, that is critical inductance, if I take the reference, if inductance value is greater than the critical inductance, if I keep the inductance value is greater than the critical inductance, it will operate in the continuous conduction mode. So inductance value is greater than the critical inductance mode. So critical inductance, it will operate in the continuous conduction mode. If the inductance value is less than the critical inductance, so it will operate in the discontinuous conduction. So the critical inductance is where it will operate in the boundary condition. So it is in between the continuous conduction and the discontinuous conduction. Continuous conduction and the discontinuous conduction. So this is very important. Now let us see the R critical value. So for example, what is the critical resistance? The resistance at which the converter is operating in the critical conduction mode. So let me take the RCR as the reference. Now let me take the RCR as a reference. Right? So what is the thing here? If I increase the R value, what happens? I minimum reducing. If I increase the R value in this expression, I minimum is reducing. So if I increase the R value, that is R critical is less than the R value. If R is less than the R critical value, if R is less than R critical value, R is less than R critical value, it is operating in the continuous conduction. If it is operating in the continuous conduction mode. Now, let us assume that R CCM is here. So now I am increasing the resistance value. I am increasing the resistance value. At some point, it will operate in the critical conduction mode. After that, what happens? So it will operating in the discontinuous conduction. Discontinuous conduction. So if I increase the R value, it will operate in the discontinuous conduction mode. If I decrease the L value, so it will operate in the discontinuous conduction mode. So this is important. This is also important. Right? Now we got a clear idea about what is continuous conduction mode, what is discontinuous conduction mode, what is boundary conduction mode, how these things are operating. So we have seen here. Now let us find what are the different conditions we have. Let us find what are the different conditions we have. What is the condition here? The I minimum should be equal to 0. The I minimum should be equal to 0. So when I minimum is 0, so IL equal to delta IL by 2. When I minimum is 0, IL equal to delta IL by 2. So here the condition will be like this. If I minimum is 0, so in this expression, IL equal to the average value of inductor current is equal to the delta IL by 2. So it is operating in the boundary conduction mode or the critical conduction mode. If IL is greater than IL by 2, and this term is greater than this term, so I minimum is positive, so it is operating in the continuous conduction mode. If IL is greater than delta IL by 2, so the I minimum will be greater than 0, so it is operating in the continuous conduction mode. Right? It is operating in the continuous conduction. If IL is less than delta IL by 2, so I minimum will be reduces. So if I minimum is reduces, so it will operate in the discontinuous conduction. Boundary conduction mode, continuous conduction mode, and discontinuous conduction. So we have these conditions also. So let us derive. So one more condition. So here. So what is the condition here? In case of critical conduction mode, so what is the condition? Let me take the buck converter here. So what is the buck converter? So here, I minimum should be equal to 0 to operate in the boundary conduction mode. So I minimum equal to IL minus delta IL by 2, so that IL equal to delta IL by 2. Right? IL equal to delta IL by 2. So what is the IL value in case of buck converter? So in case of buck converter, IL equal to I naught. So IL equal to I naught. If I replace IL equal to I naught, so which is equal to, what is the delta IL expression in case of buck converter? So Vs into D into 1 minus D divided by L. So here 2 is there, it will be the 2L. So I naught equal to, we can replace with the V naught by R. So IL equal to V naught by R. So I can replace V naught with the Vs into D. So Vs into D by R. In case of the buck converter, V naught equal to Vs into duty cycle. So these two terms will get cancelled out. So now if I write the expression like 2L by RT equal to, so replace the F with the T, F equal to 1 by T. 2L by RT equal to 1 minus T. Let me this called as a K critical. This constant will be the K critical. So let me call this as a K. So if 2L by RT equal to 1 minus D, so it is operating in the boundary conduction. It will operate in the boundary conduction. Now let us see the same expression for the boost converter. How the boost converter would be. So if I take the boost converter, so how the expression would be? So here the expression would be I minimum should be equal to 0. Whatever may be the converter, if the I minimum is 0, so we can call this as a boundary conduction mode. So if I minimum equal to 0, that is IL equal to delta L by 2. IL equal to delta L by 2. So for the boundary condition, IL should be equal to delta L by 2. So what is the IL here? I naught divided by 1 minus D. So what is the delta L expression here? So delta L already we have derived. So which is equal to Vs by L into dt. Vs by L into dt. Right? Vs by L into dt. Now you can find it easily. So by 2 is there, divided by 2 also will exist. So now, so I naught equal to V naught by R. So I can replace this I naught equal to V naught by R. So which is equal to V naught by R into 1 minus D. So what is the V naught expression in case of boost converter? So V naught equal to Vs divided by 1 minus. If I replace that, so it would be equal to Vs divided by 1 minus D into 1 minus D, 1 minus D whole square. So R into 1 minus D whole square, which is equal to Vs by L into Vs by 2L into dt. So Vs and Vs will get cancelled out. I will take the K as constant here, the same term I will take here, which is equal to 2L by RT equal to D into 1 minus D square. D into 1 minus D. So what is the K critical here? So the K critical will be the D into 1 minus D square. Let us assume that, so K critical, which is a constant, so it will vary in case of it will depends on the type of the converter. Now let us find for the buck boost converter. How it is for the buck boost converter? Let us find for the buck boost converter. How we can find for the buck boost converter? So in case of buck boost converter, again it will be the IL equal to delta IL by 2. IL equal to delta IL by 2. Now let us find. So IL value will be the I naught by 1 minus D. So here also it will be the I naught by 1 minus D. Delta L equal to Vs by L into dt. So delta IL by 2 will be the, here 2 will come. So now I naught equal to V naught by R. So I naught equal to V naught by R into 1 minus D. So into is equal to Vs by 2L into dt. Right? So what is the V naught here? Vs into D by 1 minus D. In case of buck boost converter, so it will be the V naught will be the Vs into D by 1 minus D. So R into 1 minus D whole square. So which is equal to Vs into D into T divided by 2L. So VSD and VSD will get cancelled out. So what is our condition here? 2L by RT equal to 1 minus D whole square. So in case of buck boost converter, it will be the K critical will be the 1 minus D whole square. So now let us summarize up to here. So what are the things we have derived? Let us summarize here. So here, we have find the conditions for that. So what is the conditions? So conditions for BCM. Boundary conduction mode or the critical conduction mode. So what are the conditions? The first condition will be IL equal to delta IL by 2. IL, average value of IL equal to delta IL divided by 2. If IL equal delta IL by 2, so whatever may be the converter, it will operate in the boundary conduction mode. If IL is greater than the delta IL by 2, if IL is greater than the delta IL by 2, if I find the IL and delta IL by 2, if I got the more value in case of IL, so it is called as continuous conduction mode. If IL is less than delta IL by 2, so it will operate in the discontinuous conduction. Right? If IL is less than delta IL by 2, I minimum will be reduces. So it will be the discontinuous conduction mode. So now we got the IL expression. Similarly, so let us find L critical. What is L critical and what is, so L critical, what is R critical? Let us see here. So let me take the L critical as a reference. L critical as a reference. If the inductance value is more than the, I designed the inductance in such a way that if the inductance value is more than the critical value of inductance, if it is more than the critical value of inductance, so it will operate in the continuous conduction mode. Continuous conduction mode. If the inductance value is less than the critical value, if the inductance value of the circuit is less than, so it will operate in the discontinuous conduction. Similarly, for R critical, so what is the critical value of resistance? If the inductance, if R value is greater than the R critical, if R value is greater than the R critical, so it will operate in the discontinuous conduction. If it is R value is less than the R critical, if R value is less than the R critical value, it will operate in the continuous conduction. Continuous conduction. So we have defined one more thing. We have derived one more thing, which is equal to 2L by RT, which is very important. In case of buck converter, boost converter, and buck boost converter, we have derived. So let me take the buck converter. Condition for the buck converter. So condition for the boost converter and condition for the buck boost converter. So now let us see what is critical condition mode. We have derived for the critical condition mode initially. So for example, in case of buck converter, what is the K? The K is constant, which is equal to L by RT. What is the K critical? So K critical in case of buck converter, it would be the 1 minus D. 1 minus D. So similarly, if I take the boost converter, so let me take for the boost converter. Let me separate this. So if I take the boost converter, so what is the K value? The K value will be, so 2L by RT. And what is the K critical value? So the K critical value will be the D into 1 minus D whole square. Right? So similarly, so what is the K value, which is equal to 2L by RT? And the K critical will varies, depends on the converter, it is equal to 1 minus D whole square. Right? So now from this also we can identify what is the type of the conduction mode. For example, in all three cases, let me generalize this. If K equal to K critical, so it is operating in the boundary conduction. If K is less than, K is greater than K critical, so the K critical values and K values are different for each converter. Remember that point. So it will be the continuous conduction. If K is less than K critical, it will operate in the discontinuous conduction. So this is how we can define the continuous conduction mode, boundary conduction mode, and discontinuous conduction. Now let us find the critical value of inductance and the critical value of the resistance. So now let us see the critical value, how we can find the critical value of the inductance and the critical value of the resistance, LCR and RCR. So here, let me take for the buck converter first. How can we find for the buck converter? So here, to find the converter, K should be equal to K critical. So what is the K value, which is equal to 2L by RT, which should be equal to K critical. In case of buck converter, it would be the 1 minus D. So from this I can find the L critical value and R critical value very easily. So L critical equal to, so here 1 minus D into RT divided by 2. So similarly, R critical value I can find. How can we find? So I need to find the R critical. So for that, R critical equal to 2L divided by, from this expression I can find 2L divided by 1 minus D into T. 1 minus D into T. Very simple. So this is how we can find the R critical. So no need to remember every expression. So if you know this, that is sufficient. Now Let us find for the boost converter. So again, K equal to K critical condition will be here. Let us find for the boost converter. K equal to K critical condition will be here. So which is equal to 2L by RT equal to D into 1 minus D whole square. D into 1 minus D whole square. So here, so from this L critical equal to RT into D into 1 minus D whole square, that is K critical into R into T divided by 2L. Divided by 2L. So divided by 2. So already we need to find L, right? Divided by 2. So similarly, find the R critical value. So how we can find the R critical? So R critical also you can easily find. So R critical equal to 2L divided by so T into D into 1 minus D whole square. Right? So similarly, find for the buck boost converter. So in case of buck boost converter, K equal to K critical. So 2L by RT equal to K critical equal to 1 minus D whole square. 1 minus D whole square. So from this you can find. So how you can find L critical equal to R into T into 1 minus D whole square divided by 2. So similarly, R critical equal to 2L divided by so T into 1 minus D whole square. Right? So this is how we can find the L critical value and R critical value. And if you from the data you can now if any problem is came, so from the data you can find whether it is operating in the continuous conduction mode or the discontinuous conduction mode or the boundary conduction mode. Now let us take some problems here. So let us see this. In a chopper circuit, assume that it was not mentioned here. So assume that it is a buck converter. So assume that it is a buck converter. Right? So in the buck chopper circuit shown in the figure, the figure is not given. So the input voltage as a constant voltage Vs, the input voltage Vs, and output voltage is given as V0, which as is operating in the period of duty cycle D. And what is the value of the D at the boundary for the continuous and discontinuous inductor current? So we need to find the value of the duty cycle at the boundary condition. How can we find? For example, let us see here. So here, what is if it is a buck converter? What is the condition for the critical conduction mode? K equal to K critical. So what is the K value, which is always constant, which is equal to L by R into T. So what is the K critical? In case of buck converter, it would be the 1 minus D. 1 minus D. So from that, find the D value. How can you find the D value? So D equal to 1 minus 2L by R. So to find the D value, which is the critical duty cycle, which is operating, which makes the converter operating in the critical conduction mode. So now we can find this. So from this you can answer this question. So the questions may come like this in exam, right? So D equal to 1 minus 2L by R. D equal to 1 minus 2L by R. So this is how we can find. Now let us solve the next question. So it is also buck converter is given. Buck converter feeding the variable resistive load. Load is the variable resistive load. So in the figure, the switching frequency is S, 100 kHz. Switching frequency of this switch will be given as 100 kHz. Right? Now, duty ratio is given as 0.6. Duty ratio already given, it was 0.6. The output voltage V0 is given as 36 volts. V0 is given as 36 volts. So assume that components are ideal. You need to find the value of R to make the inductor current is just continuous. Just continuous in the sense, it is here. If you observe here, it was given as just continuous. What is the meaning of just continuous? Just continuous in the sense it is operating in the critical conduction mode. It is operating in the critical conduction mode. Now let us solve the problem. So if it is operating in the critical conduction mode, So how you can find the R critical value? We need to find the R critical value. So Vs is already given, L is already given in the circuit. So here Vs is given as 60 volts, Vs is given as 60 volts, L is given as 5 millihenry. So we had all the data, we need to find the R critical. How can we find? So K equal to K critical. If you remember that expression, so that is sufficient. So which is equal to L by RT equal to 1 minus D. So here we need to find the R critical value. So because all the remaining values has given, so we need to find the R critical value. So let us find the R critical value. So R critical equal to, so 2L divided by 1 minus D, so divided by T. 1 by T we can replace it as a F. So frequency equal to 1 by time period, we can replace it with the F. So you can substitute here. First we need to find the duty cycle. Already duty cycle has given. So L value is there, F value is there. You can find the R critical. So here 2 into L. So L is given as 5 millihenry. 5 into 10 power minus 3. Right? Frequency is given as 100K. Frequency is given as 100K. 100 into 10 cube. So divided by 1 minus D. So 1 minus 0.6 is 0.4. So from this you can find. So 10 minus 3, 10 power minus 3, 10 plus 3 cancel. So 2 5s are 10. 1000 divided by 0.4, that is 10,000 divided by 4. 10,000 divided by 4, which is equal to 2500. Right? So answer is the 2500 ohms. So these are how you can calculate the R critical. So L is given as constant, but R is the variable resistance. It depends on the load. So you can vary the R value to get the boundary conduction mode. If I keep the R value as 2500 ohms, so I can get this converter is operating in the boundary conduction mode. So now let us see this. So it is a typical question. Let us see here. So here we haven't discussed the discontinuous conduction mode, but let me explain you what is the discontinuous conduction mode. So here, so it was given as buck converter because the inductor is placed on the load side. If the inductor is placed on the load side, it is a buck converter. Now, so it is operating at the duty ratio 0.5. It is operating at the duty ratio 0.5. D is given as 0.5. In case of buck converter, so what is the source voltage they have given? So 5 kHz is the frequency. Frequency is given as 5K. 5 kHz. So now Vs is given as 100 volts. Vs is given as 100 volts. Steady state current output terminals. V0 is given as 70 volts. V0 is given as 70 volts. So which of the following statement is correct? So what are the different conditions has given? So in which conduction mode this circuit is operating? We need to find in which conduction mode this circuit is operating. So let us find here. The switch S is here, the duty ratio is given as 0.5. For example, let us assume that it is operating in the continuous conduction mode. Let us assume that it is operating in the continuous conduction mode. Assume it is operating in the continuous conduction mode. So what is the Vs? 100 volts. So what is the formula for the continuous conduction mode? V0 equal to Vs into duty cycle. V0 equal to Vs into duty cycle. So that is 100 into 0.5, that is equal to 50 volts. But what happens if you observe here? The V0 is given as 70 volts. 70 volts. That means it is not operating in the continuous conduction mode, or it is not operating in the boundary conduction mode. In case of the continuous conduction mode or boundary conduction mode, V0 equal to Vs into duty cycle. But in case of the discontinuous conduction mode, V0 is not equal to Vs into duty cycle. Let us see what does it mean. Let us see what does it. For example, let me explain you the concept so that you can answer easily. So here, let me explain you the concept. Let us take the two conditions, that is continuous conduction mode and the discontinuous conduction. So understand the concept first, so you can answer very easy. So here let me draw the IL first. So how the IL, in case of continuous conduction mode, the IL will be like this, right? So the IL will be like this. So in case of the boundary conduction mode, so how the IL, let me represent with the other color. In case of boundary conduction mode, the IL will be like this. If I draw the output voltage waveform, how the output voltage waveform? If I draw the output voltage waveform, so how the output voltage? The output voltage will be, during the on time of the switch, the output voltage is Vs minus V0. It is Vs minus V0. And during the off time of the switch, it will be the minus V0. Minus V0. Minus V0 into it. If I apply this one, so I will get the V0 equal to Vs into duty cycle, which is very important. Very easy. V0 equal to Vs into duty cycle. But, so in case of discontinuous conduction mode, what happens? Let us see. In both the cases, V0 equal to Vs into duty cycle. But in case of discontinuous conduction mode, how the current will be? Let me represent with the white color first. So IL, if I draw the IL waveform, how the IL would be? So IL will be like this. It will be 0 for some period of time. Again, it will be on. IL will be like this. So it is the 0 to dt period. Let us assume that it is a dt period, and this period will be the d1t period. d1t period. d1 into t. And this off time will be the d2 into t. Let us assume that d2 into t. So what is this? How the output voltage can be drawn here? So if I draw the output voltage, 0 to dt, the magnitude will be, switch is on condition. When switch is in on condition, what happens? It will be the Vs minus V0. Right? So when switch is in off condition, that is d1t period, so which is equal to minus d1 into t. d1 into t, which is equal to minus V0. This is the minus V0. Now, so in the remaining period, so up to here, there is no device is conducting. So this voltage will be 0. This voltage will be 0. So now, so let us see here. So here, if I find so it is the dt and it is the d1. So if I find this, so what is the output voltage? So the output voltage will be the Vs into d by d plus d1. Vs into d by d plus d1. So which is greater than the, for example, let me call this as a DCCM. So D continuous conduction. So in case of the duty cycle, if you take the same input voltage and they are operating here, the net duty cycle of the discontinuous conduction mode, is greater than the duty cycle of the continuous conduction. So from this you can make this easily. Now if you know the concept, directly you can answer. So here it will be the 0.7. V0 is given as 70. V0 by Vs is, if I assume that V0 by Vs is 0.7. But how much it was given? 0.5. So if it is operating the discontinuous conduction mode, this discontinuous conduction mode duty cycle is greater than the continuous conduction mode duty cycle. So it will be the converter is operating in the discontinuous conduction mode. So now let us find critical capacitance value. So what is the critical capacitance value? How we can find? So in case of critical capacitance, so if you assume that there is a voltage ripple, so that is delta Vc, so which is equal to delta V0. So V0 equal to delta Vc by 2, by this condition, so which is the critical condition, we are assuming that this is the critical condition. So from this condition you can derive the critical capacitance value. So let us take for the buck converter. So now let us start with the buck converter. So how it can be defined? So delta Vc we have derived in the previous session. So you can take direct expression from that. So V0 equal to Vs into d into 1 minus d divided by 8 LCF square, which is equal to Vc. Delta Vc by 2 we need to do, so into 2, right? So which is equal to, here V naught equal to, we can replace with the Vs into duty cycle, Vs into duty cycle. So Vs into d and Vs and d will get cancelled out. From that, so it is Lc, right? It is LCF square. So from that you can find the critical value of the capacitance. So here, if it is C critical, critical value of the capacitance C critical. So how you can find? C critical equal to d into 1 minus d divided by 16 into L into F square. So if you know the fundamental, that is sufficient. So if you know this equation, already you have derived this equation, you know the delta Vc and every expression if you know, so you can easily find. So similarly, let us calculate for the boost converter. So what is the boost converter? V naught equal to delta Vc by 2. So V naught equal to, again it will be the delta Vc by 2. What is the delta Vc expression here? Delta Vc will be the I naught into dt divided by C. I naught into dt divided by C. Now let's substitute here. So I naught, V naught equal to, so I will replace V naught equal to I naught into R, right? V naught I will replace with I naught into R. So delta Vc expression will be the I naught into d into t divided by 2c. So I naught and I naught will get cancelled out. So we have the C critical from this. C critical, that is critical value of the capacitance equal to d into, so from this you can find it is equal to d into t divided by 2 into R. 2 into R. Or else d by 2 RF you can find like that. So this is how you can find the critical capacitance. Let us find for the buck boost converter. So if I take for the buck boost converter, again V naught equal to delta Vc by 2. V naught equal delta Vc by 2. From that, so V naught equal to I naught into R. I will replace with I naught into R. So delta Vc equal to similar expression we got I naught into dt divided by C. So by 2 is there, by 2c. So I naught and I naught will get cancelled out. From that C critical equal to d into t divided by 2 into R. So this is how you can find the critical capacitance. So here we find the critical capacitance, critical inductance and the critical resistance. So we have seen what is critical conduction mode, what is continuous conduction mode, what is discontinuous conduction mode. So we have derived the conditions for that. So the conditions are very important. So either in the gate examination or AWE examination, right? So now let us meet in the next session. So let us take the DCM, that is discontinuous conduction mode also. So after that, let us wind up the DC to DC converters. Let us take at least minimum of 50 to 60 questions. Let us solve minimum of 50 to 60 questions in the DC to DC converters, right? So this is all for today. So thank you so much. Thanks for attending the session.